hold on.
Oh.
I'm not going to get rid of my last laptop. I got rid of it when it stopped working.
Oh, then I can't see the screen very well.
Yeah, you need a retina solution.
Okay. Shall we begin? So today's speaker is Elizabeth Fischer. Elizabeth studied seismology and computer sciences at Yale and Harvard, finishing her PhD in computer sciences around 2004. She's had careers in ballet and quantitative finance, and she joined GISS around 2011. So today Elizabeth is going to be talking about her work in coupling a dynamic ice sheet model to the GISS Earth system model.
Right. So this is work. Basically, this is what I was hired here to do in 2011, and I spent the last 8 years on it, for better or for worse. So, and it's almost to fruition. So I've got a lot to. I'm going to give today a kind of a broad overview talk. I'm not going to get into the gory details on any one thing, and hopefully it'll still kind of fit within an hour. So what I'm doing is I'm coupling the GISS atmosphere with a dynamic ice model. So, currently, actually I guess still currently, the ice sheets in GISS, there's no actual ice sheet under there. It's just simulating the top 3 meters. And so what ice sheets do that's interesting, and so the current GISS model is, imagine this isn't there. And so what it can do, you can get surface mass balance. So you can, we have this model here that models stuff coming down and stuff evaporating and stuff melting. And so we can model, where is snow accumulating, where is snow melting away. And that all works pretty well. And actually, people like Patrick are making it work even better. But what dynamic ice sheet models do is they move ice sideways. On an ice sheet, you get the center of the ice sheet, you have more snow falling than melting, and then the ice piles up, and then it starts to flow sideways. And so over long periods of time, like more than 50 years, we believe this sideways ice flow is crucial to understanding the long-term evolution of the ice sheets. And right now we don't have that in GISS model, and we want it. And so the idea here is we're going to take the GISS atmosphere and this GISS, I call it the snow firn model, and we're going to stick a dynamic ice sheet model underneath it that over time can make this ice move sideways and then therefore properly model what's happening to the ice sheets. Yes?
This sideways motion, could you please explain that further? Because my impression was that ice flows downhill and that the center of the ice sheet moves slightly faster than the sides because of the drag on the sides.
That's right. Ice flows downhill. So from that's sideways. It's not moving up and down. It's moving
forward, downhill.
It's changing its XY location. In a sense, it's moving from one grid cell to another based on force that's because of the downhill motion, yes. But that's different from like what we have right now. The ice can pile up, and no matter how high it would get in the middle of the ice sheet, it would never move downhill. Yes?
So is it possible for the 3 foot, or essentially the initial, it's a 1 meter snow layer, is it possible for that to contribute to sea level rise in our model?
No, it's not. Wait, is that?
So that can't deflate down to like.
Oh wait, actually it is possible because what it keeps track of how much is melted.
Okay.
And so if you keep melting it, there's a place where all that melt stuff accumulates, and then it sends it out into icebergs. But there's no ice underneath it.
Right. Okay.
I guess maybe you could make it contribute to sea level rise. I don't think anyone would believe that because you're just looking at short-term surface mass balance. But the current model is steady state. So anything that melts off the ice sheet So we can do short-term estimates of sea level rise by looking at the surface mass balance over time and then figuring, well, if the ice sheet's lost so much mass on the surface, then that's got to go into the sea. We can do those kinds of computations right now. In fact, there's a proposal we put in to do just that. But again, beyond 50 years, nobody believes it. Although 50 years will get us to some exciting physics, right? Okay, so here's kind of a big overview of what we want to have happen. So the interesting thing here is we start out saying we want to couple a dynamic ice sheet model to the GISS model, but actually we're coupling three models together: an atmosphere model, an ice surface model, and the dynamic ice model. And it became apparent very early on that actually it was important that there are these three models. So I'm not just doing one coupling, I'm doing two couplings. Here's how those two couplings work. Is the atmosphere model, and this was already built into Model E for the most part, right? Precipitation and stuff happens in the atmosphere and fluxes. We regrid that from the atmosphere grid to E, which is the grid that this ice surface model is running on. And then we run the ice surface model, and then fluxes that have to go back, like upwelling long wave radiation, surface mass balance. We regrid that back to the atmosphere model. And we're doing this every half hour, every Model E time step. But what we also want to do here is we want to sum up these fluxes, these changes that are happening to the ice sheet on the surface and then say once a month run our dynamic ice model down here. So this cycle is spinning really quickly, and this cycle is spinning, you turn that crank occasionally. And so now you have to regrid things from E, the grid that the ice surface model is on, to the ice model grid. And then you run the ice model, and then you regrid its outputs back to both the ice surface grid and the atmosphere grid, and life goes on.
What informed that coupling time step in 1 month? Is that just practical?
Typically, the ice modelers run it at 1 year, and maybe it'll be a year. But I don't know yet. But as the ice sheet changes, we'll see later on in this talk how that changes. That you're changing the boundary conditions in Model E, and sudden changes to boundary conditions can cause non-physical effects. So the hope is that maybe by running this at a greater time step than it needs to be run, maybe we're just gradually changing the boundary conditions in a way that will be good for Model E.
So if you do this on a monthly time scale, you'd have to take the seasonal variation into account. Seasonal cycle.
Yeah.
The winter versus summer, etc.
Yeah, that's part of why monthly, not yearly.
Mm-hmm.
Because if you do a yearly, if you force the ice sheet with a yearly thing, you're just forcing it with kind of an average annual surface mass balance. And that's right. If you do monthly, you're putting this periodic signal in there, which actually maybe we don't want that. Maybe we shouldn't force it yearly. I think that'll be an interesting question to ask very soon. Okay, so I'm going to talk about the different components that are required to get a functioning coupler. Regridding, the Lynch-Stieglitz model, which we're using for the ice surface model, topo files, or boundary conditions, and then finally the coupler. And I'll talk about a couple of things we have in the meantime. So first is regridding. And what's interesting about this, regridding is a boring topic in a sense, but I've ended up putting a lot of the stuff that we want actually into the regridding. And so there's a lot to talk about here. So we're using elevation classes, and I'm not going to talk about them much, except to say that elevation classes are where you represent your function in terms of basis functions that follow elevation contours. And here's an example of my basis functions. So this is the west coast of Greenland, this jagged line here. And this is one atmosphere, one Model E grid cell near the west coast of Greenland. And here are elevation contours, these white lines. So you can see that as you come from the sea and you go inland, you see you come at the steep slope and then it starts getting up onto the ice sheet. It gets, the contours get further and further apart and they get shallower. And so within this one grid cell in Model E, that's just one basis function. You can think of it as a basis function that's 0 everywhere except inside this grid cell area where it's equal to 1, or 1 divided by the area of this. So that would be a basis function. But so now we're going to, within this grid cell, the atmosphere, we're going to chop it up into basis functions based on elevation contours. And here are 3 of them, and they're overlapping. I designed them that way. They're overlapping, so they give nice smooth stuff in the vertical. And so here is a basis function that's centered along the 950 meter contour. Here's a basis function centered on 1150 meter contour, and here's 1350 meter contour. So these are good if you're representing elevation dependent values. So if you have something that's pretty constant within a region, but it varies mostly based on elevation within that small region, elevation classes are great. So for example, that's what we have here. Surface mass balance, you expect the surface mass balance here and there will be about the same. They're not very far apart. They're both within one grid cell. But we expect surface mass balance up here near the top of the ice sheet is going to be very different from surface mass balance down there where it's raining. All within one grid cell. And so this gives us a medium scale resolution at which to run our land model, our ice surface model that's higher resolution than the native GCM resolution and lower resolution and thus more efficient and faster and easier to manage than this, say, 5 kilometer, 1 kilometer, even less than 1 kilometer that the ice sheet itself is running at. The downside of these basis functions is that they depend on the configuration of your ice sheet. So every time your ice sheet changes shape, you get a new set of basis functions, and you have to transform your model state from the old set of basis functions to the new set. So
those basis functions are roughly Gaussian centered on the contour. That's the way I kind of look at those. And you're trying to get from the GCM grid to the ice sheet.
They're not almost. They're not Gaussian centered. They're linear interpolation.
Okay.
So these basis functions are what you get if. Here's what you do. You say that within this grid cell, you run the atmosphere at different elevations. So say the natural elevation of this grid cell average is 1,000 meters. And so that's what the atmosphere sees. But now you can adjust that. You can adjust the temperature based on a lapse rate. And so you can say, well, what if this parts of this grid cell were at 900 meters instead of 1,000 meters? You say, well, it would be 5 degrees warmer. And so then this thing that fell as snow would fall as rain, and then different things would happen. So you can ask these what-if questions and run the same grid cell on a range of different elevations. And so that's what we do. And so if you run it at 1350 meters, you'll get one answer. If you run it at 1150 meters, you get another answer. And then if you say, well, what would be the surface mass balance at 1250 meters? That's halfway in between. Well, you just do a linear interpolation between the two. And these are the basis functions that you get if you do that math. So it's not a Gaussian, it's these hats, right? Boom, boom. Which is good because they don't have infinite extent. Okay. So then the next thing, I call it general conservative regridding. And there's a lot of regridding that goes on in this project. And the end of the day, I concluded there's really only one way to do conservative regridding. There's only one way, and if anyone, every regridding paper I've seen, every regridding method I've seen, either does this way, or they're wrong. Being wrong, I meaning like inconsistent, like they don't conserve, or they're not consistent between different grids. And so here's how it is. So we start by defining a grid as a set of basis functions. And I know you think, oh, I thought a grid was a bunch of squares on a map. Well, no, a grid is not a bunch of squares on a map. It's a bunch of basis functions. So we like vector calculus. And so then, once you have a bunch of basis functions, and you want to represent some kind of function on your area, say you want to make a map of surface mass balance or precipitation or something, that's this f of x. Well, the way we're going to do it is we're going to define a vector and have a coefficient for each basis function and multiply that by the basis functions and sum together. And so with a given set of basis functions, we're not able to represent any function at all over our domain. We're only able to represent linear combinations of our basis function. And this isn't anything special or new. This is how we all do it. And then we can define, well, you define the weight of a basis function. That's just, you integrate the basis function all over all area, and that's the same as the area. If you can think of grid cells as little squares on a map if you want to. And the weight of the basis function is the area of your square. And then the way we make regridding matrices is so now we want to make a regridding matrix that goes from vector space A or grid A to vector space B. And the way we do that is we take all the basis functions of A and B and take the inner products of the two of them. Again, that's very standard. And the way we take inner products of basis functions is we multiply the two and integrate them over all area. This integral right here. And so with that, we get a regridding matrix. Now it's an unscaled regridding matrix. And there's a lot of little bit of fun kind of regridding matrix algebra that goes on here. And I'm going to skip it because I don't want to get into the weeds right now. But basically, the way all regridding in this project is done is we start with two things we want to regrid between. We figure out what their basis functions are. We figure out how to take these inner products of these basis functions to make these unscaled matrices, and then we scale them. There's a way to scale them. Basically, you sum the rows or sum the columns and then divide by that to make scaled regridding functions. And the scaled regridding matrices can be used directly to regrid from one vector space to another. And so everything in this is based on this conservative regridding idea, and then just multiplying matrices together. And that sounds simple, right? I'm not even doing Gaussian elimination or preconditioning or any of those fancy differential equation things. It's just multiplying matrices. The problem is there are a lot of matrices and a lot of scale factors that have to be kept straight in order to multiply the right matrices together to get the right regridding matrix we want in the end. And that's the magic of algebra. And it has worked. Like I create these things, then I symbolically multiply them together, and then it does the right thing in the end, and I can verify it. So here's an example. Here's the simple example. So we have the atmosphere grid. That's what our GCM atmosphere runs on. There's our ice grid. Our ice model runs on. So this is a global grid, like a lat long grid. This is a local, like a local Cartesian grid in this case, or it could be something else. It could be an unstructured mesh. Finite elements have funny basis functions. And here's our elevation grid, which I showed you the basis functions for that before. So the way this works is, so you can't take you cannot take, so the first wrinkle is you cannot take the inner product of an ice grid basis function with an atmospheric grid basis function, because one of them is on the sphere and the other is on the plane. So we solve that problem by introducing two more grids, the projected atmosphere grid and the projected elevation grid. So we're projecting our GCM grid cells onto our Cartesian plane, and then we can take inner products. Or we could have projected the other way, but geometry on a sphere is harder. So now we have 5 grids, and what regridding matrices do we know how to make? Well, we know how to make these projection matrices. They're just diagonal matrices. There are 2 projection matrices we make. We know how to go between the elevation grid and the atmosphere grid, because for the elevation, no, I got it wrong. We know how to go between the atmosphere grid and the ice grid. That's just standard regridding. And actually it should be an arrow this way. We know how to go from the ice grid to the elevation grid because of that interpolation scheme I mentioned before, and there's a whole derivation of that. But the basic idea is that what we want regridding matrices between these 3 yellow endpoints. And the way we create those matrices is we find a path through this graph. And each of these arrows on this graph is a regridding matrix. And then we multiply the regridding matrices together as we go along that path, and that gets the end matrix we want. And that's what's being used in the coupler. Okay, so of course it doesn't stop there, because there are more interesting effects, more important things that this coupler needs to do that we're going to cram into the regridding. So one of them is smoothing. And so the problem is that if you just use standard elevation classes, you get the imprints of your atmospheric grid cells onto the surface mass balance and the fluxes that you're sending to the ice model. And that causes kind of non-physical effects and ice cliffs inside the model, inside the ice model. And ice models really don't like that. And they can be fragile, and if they can throw a hissy fit and just not converge one time step and not run, and they just don't like discontinuities or almost discontinuities in their input. So we want to smooth it. And the clever thing, you say, oh yeah, we'll just put a Gaussian smoother over this. But this is more clever than a Gaussian smoother because great elevation classes give us this fine gradation around here, around the edges, where you see that even though this is a smooth field, it needs to vary quickly going sideways. And if you just apply a Gaussian smoother, you will smooth out exactly the resolution, the detail you're trying to preserve and create using elevation classes. So it's this 3-dimensional Gaussian smoother where it smooths in the XY direction with a large radius, say 50 kilometers, 100 kilometers in the XY direction, but only say 50 meters in the Z direction. And so that way, smoothing in elevation classes, we can get this stuff as smooth as we want while maintaining the details here. So great, we were very clever. We figured out how to make a smoothing matrix.
Sorry, just because the comment is there, you indicated before that that process is not necessarily conservative.
Oh yes, it's not conservative. Yeah, so I went to all this work to figure out how to make all these regridding matrices conservative. That is correct. So the previous prior art, just this problem, they were very not conservative, like off by a couple %. And there's no reason to shoot yourself in the foot on math, needlessly. So I made that conservative. But there's really no way to get the smoothing conservative. But the degree of non-conservation I have is more like the order of 10 to the -4th. And so, I've done the best effort on my regridding, and then I get this compared to other groups, very small non-conservation, that then I'm just gonna just do a global conservation correction, which is kind of wonky, right? So you regood from here to there, and you take the sum of this and the sum of that, and you see that this one is 1% bigger than that one. So you multiply this by 1.01, and then it's fixed.
It's a uniform fix everywhere.
Yeah, uniform fix everywhere. So it's, yeah, that's what people do when things aren't conservative. And you know, I was at a conference, you know, and finally I said to someone, I said, you know what, I think I'm going to have to not be totally conservative. And this is someone who'd been seeing my work for the past few years, and he said, yeah, I had a feeling it would come to that. So.
But this has to do with, like, I mean, like you said, globally you can be conservative, but just locally, it's local conservation that you're struggling with.
Well, conservation is conservation. It's that you can always fix conservation by applying global corrections.
Right.
But part of the point of this project, because we are here at GISS, is to be conservative. And so at every step of the way, I have worked to be as conservative as I know how to be, as human knowledge can do it. And I think I'm there. If somebody else can figure out how to make this conservative, I'd love to hear it. So the next thing, this is another non-conservative thing. The Model E ocean, okay. So this is background information. You know, in Model E there are 4 ocean grid cells per atmospheric grid cell. And every ocean grid cell must be all ocean or all land. And so what this means, that the edge of our ice sheet, I need an eraser and a pen. Yeah. So the edge of our ice sheet then, here's the problem. If you have an ocean grid cell like this, and here's your ice grid, and your ice model decides it wants to live, that this is the extent of the ice sheet. Well, then the ice model says there's ice here, and then the GCM says, well, we can either be all land or all water, and there's not much land in this grid, so it needs to be all water. So the ice model, PISM, says there's ice here, and Model E says there's not ice there. And so what Model E does is it rounds these ocean grid cells. So with this one, it would say, oh, there's not much land there, so that's going to be all ocean. Whereas another one, it would, you know, say there's your coastline, and there's just a little bit of water. Model E will say, oh, that's mostly land, so let's just make it all land. And so if you have some ice in this grid cell, you have to kind of bigify the ice. So you say, well, this started out as 80% land and 20% ocean. Now it's 100% land, so everything gets multiplied by 25%. So you have 25% more. Model E now thinks there's 25% more ice in there than PISM does. And meanwhile, over here, PISM thinks there's ice there, and Model E thinks there's no ice at all. So the exciting part of this is that that's this rounding thing. So the exciting part of this is that Model E and PISM think that the ice sheet is not just different in terms of they're on different grids, so they look a bit different, but it's not that they're looking at the same ice sheet through different glasses. They're actually looking at different ice sheets. And as the model run continues, the Model E ocean can never change. And so if you have tidewater glaciers that retreat, you know, those can't become ocean at that point. It just kind of has to stay the same. So potentially the ice sheet and the ocean can diverge a little bit more as the coupled run continues. And so we have to have a way to deal with this divergence between the two. And then the last thing this does is so we're going to compute all our regridding and boundary conditions on the ocean grid, and then we're going to regrid to the atmosphere grid because of this all or nothing thing on the ocean grid. So we typically get atmosphere grid cells near the boundary of the ice sheet that are 1/4, 1/2, 3/4, or 100% ocean or land. But it's not exactly 1/4, it's approximately because of the way the Model E grid cells work. Okay. So this doesn't have quite all the complexity. This has most of the complexity of what's going on, how we create the regridding matrices. So right, every time we have a new thing, basically have a new phenomenon that needs to be taken into account, we just invent a new vector space. And that's I've shown here. I haven't shown the projections from before. They're kind of hidden away inside one of these. But so what I've shown here is, okay, there's our ice grid. This is kind of a rough ice grid. So this takes account for the smoothing. So we go from a rough ice to smoothed ice. There's a matrix there. AOP this is the ocean grid. This is elevation classes on the ocean grid. Now P means from the PISM point of view. So that means the ice sheet you see here is simply a regridded version of the PISM ice sheet. It hasn't gone through this rounding process. But now we can go through here to a round. So then the ALM is the ocean grid in that Model E sees. So something in this vector space is a version of what the PISM sees, and then you do the rounding process and fudging those weights to get to AOM, which is the ice sheet that Model E sees. And then, of course, AM, we have to convert that to the atmosphere grid, so we regrid that up to the atmosphere grid. And same thing over here on the elevation class side, EOP, that's your elevation grid with respect to the ocean, the original ocean grid cells. And here, if we EOM, this would be the elevation grid with respect to ocean grid cells with the rounded ice sheet. And then EAM, this is what our ice surface model actually runs on. So this is elevation classes on the derived from the full atmosphere grid with the rounded ice that Model E sees. And so now we have this big complicated graph. We figured out how to build regridding matrices between all of them. And what we want is, again, this is the vector space the PISM runs on. This is the vector space the atmosphere runs on. This is the vector space that the ice surface model runs on. And so we find paths through this graph and multiply matrices together to get these. I've shown these dotted red lines. These are the matrices we actually want. And we get them by taking the matrices we know how to compute and just chaining them together and multiplying them up, and it works. And that's the magic of algebra. You get these symbols that actually represent something physically meaningful. So I'm not going to talk anymore about how I figure out each of those arrows. Any questions on this? So this is translated into a few hundred lines of indecipherable code unless you understand these algebraic symbols and stuff, and then it all makes sense. Okay, so the Lynch-Stieglitz model. The Lynch-Stieglitz model was developed by Mr. Lynch-Stieglitz, who was at GISS. It's really from 1994, so it is not a cutting-edge model. And it is already used in Model E, for example, for snow that falls on land, and I believe also for on top of sea ice. And it is a basic layered model of stuff. And so the problem was that original snow firn model that was used for ice sheets in Model E was not suitable for coupling anything below it. I tried. I stared at the equations for many months. Couldn't do it. So we threw out that model, and in its place we put the Lynch-Stieglitz model over land ice, as well as the other places it's used in Model E. And that can be run. That can be run without this coupling. You can just, whatever you're doing with Model E right now, you could replace. You could run the Lynch-Stieglitz land ice instead of the old land ice, and it'll give reasonable results. Luckily, Lynch-Stieglitz is also more flexible, more configurable than what we had before. And so what we're going to do, right, so remember that picture that we run the top of the things at high frequency and down below the low frequency. So the heat equation is run at high frequency in the Lynch-Stieglitz model and low frequency down below. And so if you think about it, if you have a domain, level ground, you have a domain, and you're going to force it with the heat equation. So you're going to run the heat equation in this domain, and you're going to force it with some kind of periodic forcing. Now this is one of the classical kind of differential equation problems that, of course, people looked at before they had computers. And so what you will get is you'll get something like this. Okay. So right, if you have a domain that you're running the wave equation in, and you force it with periodic forcing, you'll get these waves that travel basically infinite distance, right? So you'll get waves that don't really attenuate in a perfect wave medium. But we're not running wave equation. We're running the heat equation. And when you do this in the heat equation, you get the same thing, except it's an exponential decay. So the deeper you go, the amplitude of this periodicity diminishes exponentially. But the period stays the same. So it's like in the wave equation. So you get this periodicity, all the way down forever. In theory, it's just exponentially decaying, which means in physical reality you don't get it. And so what you need to do, so what we want to do here is we want to cut this. We're going to run Lynch-Stieglitz. We're going to run the Lynch-Stieglitz model in the top part of this, and we're going to run the dynamic, we're going to run PISM down below. Now PISM runs at low frequency, like 1 month or 1 year or something. So that means that any higher, if you force something that runs at low frequency at high frequency, you're cutting out all the high frequencies, right? So that means that where we match the Lynch-Stieglitz model, our snow firn model, to the dynamic ice model, we're going to be cutting off our high frequencies at that point. And so we want the Lynch-Stieglitz model to be thick enough that we don't have any high frequencies of an amplitude we care about by the time we get to the bottom. And that's typically thought to be 10 to 15 meters thick. And so we have this weird non-physical system here where we have one set of physics running out here that has very high fidelity of the heat equation and things, and surface mass balance, but ice can't move sideways. And then down here, it knows how to move ice sideways, but it can't do anything at high frequency. Yes?
Is that assumed firn thickness thickness realistic for the actual ice sheets?
Fern thickness, there is
No, what you have, you say that this heat penetrates in this model. This model is basically for the snow and fern.
Yes.
Yeah, so it's a 10 to 15 meter depth that your heat signal is penetrating. Well, what about the actual or more realistic thicknesses of that layer?
Well, the heat signal penetrates forever, right? If you heat up the top, you know, if you change the climate and you heat up the top, eventually it'll get warmer down here inside of PISM.
Yeah, but you say you're cutting it off at a certain level.
Yeah, we're cutting off the high frequency energy. It's like a capacitor, right? If you take a capacitor and you drive it at high frequency, you will get low frequencies out the other side. You know, energy will still pass through, but you will not get high frequencies. And so right, if we heat this up, you know, this is thermally coupled right here. Heat can flow between these two, but don't expect to see diurnal variation looking inside of PISM. And because PISM, because it runs at low frequency, it cannot represent diurnal variation. So you'd better not force it with anything that high frequency, or else you won't get a physical result. And so essentially what we're forcing it here with something that's with signals that are low frequency, because the high frequencies have been filtered out by this being deep enough. Right, so it's important to remember there's real life. You know, real life is everything runs at infinite at high frequency, and fern gradually turns into snow over a process of about 50 meters or more. It gradually turns into ice. Here, we're having one model that's 15 meters and another model that's the rest. And you know, if PISM can manage fern, we'll let it manage fern. We can give it fern. You know, this 15 meters down, it's not going to be fully compacted into ice yet. But if PISM cannot manage fern, we're just going to magically make it ice when we give it to the dynamic ice model. So it's important to keep in mind, again, there's this is physically an invisible boundary where between these two models. We're passing stuff between these two models, but in real life, in model life, it will make a difference. It'll change your answers. In real life, it shouldn't make a difference because there is no actual boundary here. It's not like the MOHO or any of that stuff. Okay?
So
Yep.
we have a question from someone on WebEx. They asked us, it might probably refers to something previous. They asked, what's the input data for the elevation grids?
The input data?
For the elevation grids.
I guess what does input data mean?
The source of the topo data.
So how do I get the topography? It's eTopo1.
Okay.
Yeah. The other things that there are lots of things that are represented on the elevation grid, and they come from different places.
Okay.
Question two. And CS is basically a perfect insulator after like 2 meters of thickness. Why is it so much greater for wet ice?
Because it's not a perfect insulator after 2 meters. It's just the heat is not able to get past those 2 meters.
Right. Yeah, exactly.
Yeah. I mean, when people talk about snowball Earth, sometimes they've talked about the possibility of the ocean freezing all the way to the bottom. That's not going to happen in 2 years. But, you know, if you make it cold enough and you wait long enough, it will happen.
I'm just a bit concerned about time, so maybe 15 minutes?
Okay. All right. Okay, so the next thing we do, basically, the ice model, the PISM does not conserve energy. It conserves mass, it does not conserve energy. And it's obvious when you look at how it works, it doesn't conserve energy. So how are we going to conserve it with Model E? Well, what I do is basically I set up this energy budget. You know, I look at everything going into PISM, everything coming out of PISM. I sum them up. They all have to be equal. If they're not, whatever the difference is, that epsilon is what PISM didn't conserve. And the idea is that the coupler can then measure PISM. It can measure what PISM did and how much PISM didn't conserve, and then again do whatever kind of global energy corrections it wants to based on that. So this is, I guess this is just a list of what's in that energy budget. Basically, there's mass moving around, energy related to mass moving around I call enthalpy. There's heat fluxes at the bottom, you know, with the Earth, geothermal heat fluxes. There's heat fluxes with our Lynch-Stieglitz model. You know, we're not tracking gravitational potential right now, but in the end we have to deal with that. So here's just a few examples I had from PISM of my energy budget. So right, the energy budget is different terms, and we can look at each term. So here's this is mass budget. So here's surface mass balance. You see that it's there's a snowstorm here. This is probably a 1 month of run. So there was a snowstorm here, and then there's some melting around the edges. So that's all just like we want. Here's internal advection. That's ice moving sideways. So you see ice moves very vaguely sideways. You can see a little very light stuff around here. And it moves faster sideways towards the edges where ice streams kind of coalesce and move faster. So this is PISM doing, this is the whole purpose of PISM. It has one job, is to move ice sideways. And here we see it's doing that job. Basal runoff. Well, PISM also melts ice down at the bottom of the ice sheet, and here's where we see that runoff. You see these are different scales. This is 10 to the minus 7th. This is 10 to the minus 3rd. And then we can do a mass budget, and you see here's our error term when we close the mass budget and see how much PISM did not conserve. And what we see is there is a pattern. It's different. It's bigger in the interior versus the exterior, but within that large-scale pattern, it's kind of pluses and minuses and no discernible pattern there. And it's also 10 to the minus 16th, which is our numerical precision. So this is what we want to see, is we conserve mass to numerical precision. Here's our energy budget. Again, surface mass balance is mass moving, but there's enthalpy involved with that. Same thing with energy. Same thing with all these three. These are the same as we just saw, except in enthalpy space. And you know, we got a somewhat different. And here it shows that PISM was not conserving energy. It was not this bad. This was 218 watts per meter squared. That's been fixed since then. But even so, PISM does not conserve energy. But this graph right here, we can send back to Model E, regridding, of course, to Model E grids, and therefore understand how much we're not conserving within each Model E grid cell and decide what to do about it. Topo files. So I redid, Gary Russell's topo generator that I think it hasn't been run for 15 years, practically, based on some artifacts in the code. Maybe it has, I don't know. But I took that and I changed its input files from eTopo2, the 2-minute, to eTopo1. I guess just because since 15 years later we have better data. And I used the same algorithm and generated topo files that are basically the same, except they generate the elevation class profiles. So using these eTopo1, I was able to generate elevation classes for all ice-covered regions of the globe, which is exciting because now in standard Model E, even without the Lynch-Stieglitz model, we can just use this new topo file and get better surface mass balance and more precise surface mass balance for all, for Baffin Island, for Antarctica, anywhere there's ice, for Svalbard, even Greenland. Even without the two-way coupler, we can get that.
Actually, so the Topo 1 that we used was probably downloaded maybe like 6 or 7 years ago. And it didn't have the ice like in the Himalayas or the Andes. Has that been corrected?
Right, I only care about Greenland, so whatever crazy things ModelE was doing elsewhere in the globe, I didn't want to mess with it. But then the cool thing about my topo files is I have cut out Greenland in them. So it has a very high resolution outline of Greenland, and so it can cut that out of whatever topo file it reads in. And then, once I've removed Greenland, I feel like, you ever seen Despicable Me, the movie? You know, I stole Greenland. Then I can put in my own Greenland. And I put in my own Greenland, that's the Greenland based on whatever PISM created. And that's what we need with our coupling, because we need PISM's version of Greenland in with our boundary conditions we're running the model with. So here's an example. Okay, here's the ZATMO. So here's the global bottom of the atmosphere elevations that we got out of my new topo files, and you see it's exactly what you think it should be. Except, you see here's this high elevation area in Antarctica, but then you look there and you say, oh my gosh, what happened to Greenland? And yeah, this plot program, Panoply, insisted on putting an outline there anyway, even though there's nothing there. This is all sea level. I stole Greenland. But then down here, this is ocean depth. You see, I didn't completely steal Greenland, because you see there you can still see continents look brown, and there you still see something brown where Greenland used to be. So that's because I set any place where I took away Greenland that used to be land, I set the ocean depth to 300 meters. And I know that's a little wonky, but I also know that I'm going to be putting in my own Greenland that's approximately the same shape. So it'll be okay. The 300 meters was about what the continental shelf area around Greenland was. So once I've done that, because I don't have it wouldn't have been an interesting picture. It would have looked the same as the original. You know, I take the PISM Greenland and I can regrid that back into elevation space and put it in there. Okay, so now the final coupling. Here's what we do. We're going to run ModelE. We're going to accumulate a bunch of fluxes. Mass and enthalpy fluxes to the bottom. Heat flow across the bottom of the model. And then we're going to advect mass across this invisible boundary as needed to keep this layer 15 meters thick. Unless there's no ice below, then we let it melt. Then it's no longer part of two-way coupling. So then we're going to take all these values that we accumulated on the elevation grid, we'll regrid them to the ice grid using that, remember that big fancy graph of regridding matrices all over the place? Those are the matrices we use here. And then whatever mass we took away from Lynch-Stieglitz, now we give it to PISM. Any meltwater issues, and the energy flux through that invisible boundary, we use that as a boundary condition for PISM. Now we compute the total energy of PISM, then we run PISM for a month, then we compute the total energy again, so we can get those energy conservation pictures I was showing you before. And then then based on the current PISM state, we create a new Greenland and stick that into our topo file, and so we create new topo file for ModelE based on whatever state PISM Greenland is in right now. And then we take all that stuff and we regrid it, all those fluxes and everything, we regrid them all, pass back to ModelE. So we pass back the regridded fluxes, we pass back the changes in our topo file, but ModelE actually changes its own topo file elsewhere, so we're not going to touch that. We're only going to touch parts near Greenland. And we also have ghost grid cells that we use in case the ice sheet moves into them or out of them. And then finally, we have to compute the regridding matrix between our old set of elevation classes and our new set of elevation classes. And we do that the same as we compute all regridding matrices, is by taking inner products of the two sets of basis functions, and we saw the basis functions at the beginning of the talk. And then when it goes back to Model E, we regrid our Lynch-Stieglitz state, and we can move on and repeat the cycle. And so that's how it works. And this two-way coupler is almost finished. Until then, we have this Lynch-Stieglitz model in place. That provides an excellent platform for adding more physical processes to SMB, like albedo effects based on age of snow or different things that happen to the snow, blowing snow possibly. Talked with Patrick Alexander more about that. We can also do one-way coupling. We can use elevation classes to generate SMBs for specific climates, and then drive an ice model with that SMB offline and see what happens to the ice model. So we can look at possible future scenarios, but probably not a very realistic one because there's no feedback. And we can also, for example, look at how changes. I think changes in boreal vegetation can have a big effect on the ice sheets, and we should be able to see it by, like, if we change the vegetation structure in Model E, we should be able to see changes in the surface mass balance in Greenland, among other things. So, and then the big limitation of this is I haven't said the A word at all. I haven't said Antarctica in this talk, and that's because successful modeling of Antarctica, you need subshelf melting, because a lot of what's melting the Antarctic ice sheet right now is this warm water coming in and melting under ice shelves. And so, yes, this coupling works in Antarctica just fine, and elevation classes work, but I would not believe any answer I'd come up without also having subshelf melting. And Craig's going to get that for us next week. So.
Would you care to elaborate on how changes in the boreal vegetation would affect Greenland's ice sheet?
Yeah. Well, it changes the albedo a lot.
Oh, so it'd be the albedo effect mainly.
Yeah.
The other thing is that when this model is...
But you're changing albedo effect over a large area, North America, Asia. If these areas of currently or tundra become forested, that will greatly lower the albedo over a large area in the Arctic and subarctic, which will, of course, will have an effect on Greenland.
Mm-hmm.
And we don't know what. And obviously, we think it would make things warmer and probably cause more of Greenland to melt. It could also, of course, affect atmospheric circulation and rainfall patterns, which could also have an effect on Greenland. Like, for example, southeast Greenland has very healthy glaciers, not because there's a lot of melting there, but there's also a lot of snowfall.
Mm-hmm.
Some predictions have even shown that that in the near future we expect the glaciers in southeastern Greenland to increase because of changes in rainfall pattern could bring more moisture there. So, so the health, whether ice sheets grow or shrink depends on the balance between snowfall and melting.
So you mentioned the A word right at the end, and subshelf melting. Does PISM handle, so Greenland mass balance is half melt, which presumably this is a part of this regridding, but the other part is calving. So does PISM handle, does it have an arbitrary calving?
Yeah, it has calving.
Okay.
It's not state of the art, I guess.
Right, but it's there.
I mean, yeah, there is some calving in Greenland, and you know, in the near future, there will be very little calving in Greenland.
How computationally expensive is the whole system, the regridding plus PISM?
Everything I've shown here is negligible compared to Model E.
So whether you run it monthly or yearly, then there's no.
Yeah.
So this thing, this linked sequence model, is that what you call the first slide you showed was that was the surface ice thing model. That's what you call it. It's the same as Lynch Stieglitz.
Yeah.
Okay,
So
that's the Lynch Stieglitz.
I ripped out the old 3-meter model here, and I put Lynch Stieglitz in its place.
Craig, wasn't there an ocean model meeting about a different surface thing? Which I don't. It started with P or something. It wasn't PISM though. PSEC or something.
Pico.
What?
Pico.
Pico. Yeah. What's the story? What's is that?
PICO is a parameterization for floating ice shelf melt.
Okay. Okay. So that's a different.
And it's included in PISM. Right?
Oh, it is.
Yes.
I
Yeah.
see.
So you know, it won't make our it won't make our model magically work. Someone still has to look at it and think about it and couple it properly with the Model E ocean. But it's I think it could be a really big step forward. And until very recently, there were no just plausible subshelf melting parameterizations.
We go.
I was just going to ask how close do you think the field is to a dynamic fern in an ice sheet model? Is that far, or is that?
I mean, how close is this project to a successful two-way coupling?
Well, I was thinking more of like, yeah, well, sort of, but I mean, like getting a dynamic. So, Lynch Stieglitz model, getting a part of the problem with sea level rise is that the interior of the ice sheet can conceal a lot of mass in the fern. And so I guess the question is like, at what point do you have two-way coupling and a proper fern model?
That's never going to happen.
Okay.
No, I think we have to kind of, at this point, content ourselves with the fern just magically turning to ice when we give it to the ice model. I mean, the ice models are very inadequate in a number of ways. For one, they think the Earth is flat. Which I don't know any other way to put it. They think the Earth is flat, and so, for example, for something like Snowball Earth, with these hemisphere covering glaciers, that's already a problem. Even with what we have here, we're dealing with these projections. Why are we dealing with projections? That's an artifact of having built the ice model in the wrong coordinate space. And PISM doesn't conserve energy. PISM doesn't know how to deal with fern at all. It only deals with ice. So yeah, there are lots of, and also PISM doesn't do outlet glacier areas very well. It's basically for the interior of the ice sheet and the general dynamics of what's going on. So there's certainly a lot of improvement that could happen in ice models. But when I go to these land ice working group meetings and they say, hey, I'd really like an ice model that runs in spherical geometry, people just laugh at me.
Okay, I think we should probably wrap up at some point. Just like to thank you a little bit.
Honest with you, I guess the Topo 1 does have the ice thickness over Antarctica and Greenland. Do you use that at all?
Yeah.
I mean, because it shows like in Greenland, there's a ring of mountains along the coastlines, and the interior is actually below sea level. Things like that.
Yeah, I get all that out.